In this video, I would like to continue the discussion of continuous probability distributions and discuss sampling distributions of statistics. Now, the word statistics here isn't the subject, it's the characteristics of a sample of data. So sample mean, sample standard deviation, and so on. Now, a sample distribution is a distribution of all possible values of a sample statistic for a given sample size. So we have a sample and we choose a value of n, the sample size. So for example, the sample distribution of the sample mean. Let's say we have a sample of values. Let's just say our sample is 1, 2, 3, 4. Then we could take, so this is, let's say this is our population. There's only 4 numbers in the population. And we're going to take samples of size 2. So we could take every possible sample of size 2. So for example, sample number 1, we could take, I don't know, a 1 and a 3. And so the sample mean, or the first sample mean, would be, well, the average of 1 and 3 would be 2. Another possible sample could be the 3 and the 4. And the mean of that sample, the mean of sample number 2, or the average of 3 and 4, would be 3.5. And we're going to sample with replacement, so another sample mean, or another sample could be 2 and a 2. And so the average of that sample would be 2. So here's 3 possible samples and 3 sample means. Now the sample distribution of the sample mean is what we get when we get all possible sample means. So every possible sample of size 2, I only have 3 of them here, but there's more possible samples. There's actually 16 of them because we have 4 options for the first number in our sample and 4 options for our second numbers. 4 times 4 is 16. So there's actually 16 possible sample means. All right, so that's what we're going to be discussing here. So for example, let's say you have 50 students from your college and you're looking at their GPA, their grade point average. So there's a lot more than 50 students in the college, and we're picking samples of size 50. Well, our data is a list of 50 numbers, and our sample statistics are the means of those samples. So we have our first sample of 50 students, our first sample mean. Then we take another sample of 50 students and another sample mean, and so on. Now it's a huge list of sample means because there's many possible samples of size 50 possible from an entire college which has thousands or tens of thousands of students. So let's look at a smaller example similar to the one I discussed a couple of slides ago. So let's say I used 1, 2, 3, 4, but let's say we have 18, 20, 22, and 24. Okay, so our distribution of the data, well, the value 18 accounts for 25% of the population. The value 20 accounts for also 25%, or 1/4 of the population, and so on the 22 and the 24. And we could apply our formulas for a population mean and population standard deviation. And the mean, or the average value, is 21, and the population standard deviation of 18, 20, 22, and 24 would be 2.236. So now let's look at all possible samples of size 2. And like I said earlier, there's going to be 16 possible samples because we have 4 possible values for the first value in our sample and 4 values for our second. Okay, so for example, 18 and 18, that's one possible sample. 18 and 20, That's another possible sample, and so on. Okay, so once we list all of the possible samples of size 2, 16 possible samples with n equals 2. Now we could do this with n equals 3 if you want also, but we'll just do n equals 2 right now. And for each one of those 16 samples, we could calculate the sample mean of those samples. So sample number 1 has a mean of 18. Sample number 2 has a mean of 19, and so on. So these 16 values on the right, each one of these is an X bar. And so the distribution of sample means looks like a normal distribution. So we started off with this uniform distribution. Let me go back a couple of slides. The data itself had this uniform distribution. But when we start taking every possible sample, and look at every possible sample mean, that distribution, which was normal for the data, is actually, which is uniform for the data, is actually normal for the distribution of sample means. And then we could do the same thing as before, calculate the mean of the sample mean. So we have now, instead of the data, we have these 16 values. These are the sample means. And we could calculate the mean and the standard deviation of this set. And so for the population, we had a mean of 21 and a standard deviation of 2.236. But when we take the standard deviation of the sample means, we get a smaller value. We get 1.58. We'll talk about why this is true a little bit later, but you'll see that the mean of the sample means is equal to the population mean. And that's interesting. So it looks like the means, the sample mean is an unbiased estimator, meaning the average of all the sample means is exactly equal to the population mean. And as the sample size increases, the standard deviation of the sample means actually gets smaller and smaller. And so this standard deviation of the sample means, we call this the standard error of the mean. And the reason we get a smaller value is because we take the standard deviation of the population of data and divide it by the square root of n. So on the previous slide, we had a population standard deviation of 2.236, and we divided that by the square root of 2 because 2 was the sample size. So if you take, now let me go back one slide. If you take this standard deviation of the original data and you divide that by the square root of 2, you get the 1.58. And that's where the 1.58 is coming from. And as I said, as the sample size increases, the standard deviation of the sample means decreases and gets smaller and smaller. So for the distribution of sample means, so now we have, and this is not for the original data. So you have to start with data and then you collect all the sample means of that data. And then once you have those sample means, the distribution of sample means, these are the X bars. I'll say X bars plural. The mean of the X bars, the mean of the sample means is equal to the population mean, but the standard deviation of the sample means is smaller. It's equal to the population standard deviation divided by the square root of n. Right? And so if we want to convert an X bar to a z-score, so to convert an X to a Z, we have the formula z equals x minus the mean, x minus the mean, divided by the standard deviation. We discussed that in a previous video. But we're not converting an x value to a z-score. We're converting an x bar. We're converting a sample statistic to a z-score. Right? So we can replace the, we can replace, that should have stayed there. We could replace the x with an x bar, because that's what we're converting. We could replace the population mean with the mean of the sample means, because they're equal to each other. And we could replace the population standard deviation with the standard error, which is the standard deviation divided by the square root of n. And if we do that, we get this. This is our formula for converting an x bar into a z-score. And the reason we do this is because we're going to be calculating probabilities later. Okay. And as I mentioned, because the mean of the sample means is equal to the population mean, we say the sample mean is an unbiased estimator of the population mean. Right? And additionally, if, and this second statement is an if-then statement, if the population is normal, then the distribution of sample means is also normal. And we'll see later in my next video on the central limit theorem that sometimes, even if the population is not normal, the distribution of sample means is. Okay. So what this tells us is that the sample means, by being an unbiased estimator, the sample means target the population mean. And this leads us to a very important theorem in statistics called the central limit theorem. And that's going to be the topic of my next video. So this is going to sort of lead into that. We're going to have to, in my next video, we're going to sort of extend on this slide. The fact that the mean of the sample means is equal to the population mean, and the standard deviation of the sample means is equal to the population standard deviation divided by the square root of n. And we're going to also use this conversion from x bar to z-score. All right, so that about does it for this video. In my next video, I'll also talk about which sample statistics are unbiased estimators, or which sample statistics target the population parameters and which ones don't. So it turns out the mean, the variance, the proportion, these are unbiased estimators, whereas the median, the range, and the standard deviation are not. They are biased estimators, meaning if you take all possible standard deviations from all possible samples and you average them out, you're not going to get the population standard deviation. Okay, that does it for this brief discussion on sampling statistics, or sorry, distributions of sampling statistics.